Welcome everyone to Catalyst Conversations, where we bridge the gap between cutting-edge technology and business strategy. Today, we're diving into a fascinating and frankly crucial topic: large language models, or LLMs, and their surprising struggles with making decisions. We have a fantastic panel of experts with us today to unpack this. We've got leaders spanning business strategy and deep technical AI research. Let's jump right in.
Thanks for having me. It's a really timely discussion. From a business perspective, the potential of LLMs as agents, systems that don't just process information but actually do things, make decisions, interact with systems, it's enormous. We're talking automating complex workflows, hyper-personalized customer interactions, dynamic resource allocation. The list goes on. But there's a gap. We see these amazing demos, these flashes of brilliance, yet deploying them robustly in high-stakes decision-making roles, it's proving much harder than the initial hype suggested. There's definitely a disconnect between what they know and what they consistently do.
That's a perfect setup. This knowing-doing gap is something highlighted in recent research, alongside other challenges. Expert 2, can you break down these core failure modes that researchers are seeing when LLMs face decision tasks?
Absolutely, the paper we're drawing from identifies three main culprits, and they're quite intuitive when you think about it. First, there's greediness. The LLM finds an option that gives a decent reward early on and just sticks with it. It becomes overly focused on exploiting what it already knows works, even if it's just mediocre, rather than exploring potentially much better options. Think of it like always going to the same okay-ish restaurant near your office because you know you won't hate it, but you never discover that amazing place just 2 blocks further away. The LLM gets stuck in a local optimum.
And this greediness, as the paper shows, means they leave a huge part of the potential action space unexplored, sometimes over 50%. That's a massive missed opportunity, whether you're talking about optimizing ad spend or finding the best move in a game.
Exactly, the second issue is frequency bias. This one is particularly noticeable in smaller models, like the 2 billion parameter ones tested. They tend to just copy the action that appears most frequently in their recent history or context, regardless of whether it led to good or bad outcomes.
So, like echoing the most popular opinion in the room, even if it's wrong.
Precisely, it's almost a cognitive shortcut gone wrong, likely an artifact of how they're pre-trained on massive text datasets where mimicking common patterns is rewarded. It's less about reasoning, more about pattern repetition. And the third, as expert one mentioned, is the knowing-doing gap. This one's almost philosophical. The LLM, especially with chain-of-thought prompting, can often articulate the correct strategy. It can literally write out, step by step, how to solve the problem, like calculating optimal moves using a known algorithm like UCB in the bandit tasks. But then when it actually comes time to select the action, it often ignores its own brilliant reasoning and defaults back to a simpler, perhaps greedy choice. The paper found models generating correct rationales 87% of the time, but then only following through with the truly optimal action based on that rationale about 21% of the time. It knows the path but doesn't walk it.
Wow, 87% knowing versus 21% doing. That's stark. It's like knowing you need to save for retirement but spending the paycheck anyway. Expert 3, the paper mentions model scale playing a role, particularly with frequency bias. Can you elaborate?
Yeah, that was an interesting finding. The smaller 2B models were significantly hampered by frequency bias, just copying common actions. The larger 9B and especially the 27B models largely overcame this specific bias. They didn't just blindly copy frequent actions anymore. But and this is key, getting bigger didn't automatically solve the greediness problem. Even the 27B models, while smarter in some ways, still got stuck exploiting early wins rather than exploring sufficiently. So, scale helps with some naive failure modes, but not the fundamental exploration challenge.
And this is where chain of thought, or COTI, comes in. COTI prompting asks the LLM to think step by step before giving an answer. It definitely helps, as the paper confirmed. Models using COTI explored more and performed better than those without it. It essentially forces the model to engage its reasoning capabilities to simulate a thought process. But, as Expert 2's stats on the knowing-doing gap show, COTI alone isn't a magic bullet. It improves the knowing part significantly, but the doing part still lags behind. The reasoning doesn't always translate into action.
Okay, so we have these inherent weaknesses: greediness, frequency bias, the knowing-doing gap. And while scale and COTI help, they don't fully solve it. This brings us to the core innovation proposed in the paper: reinforcement learning fine-tuning, or RLFT. Expert 2, can you explain this approach?
Right? So if the standard LLM is prone to these bad habits, the idea is to explicitly train it to be a better decision maker using reinforcement learning. RL is the classic paradigm for teaching agents to maximize rewards in an environment. The clever part here is how they do it. Instead of just rewarding the final action, they fine-tune the LLM based on the rewards received after it generates a chain of thought rationale and an action. The RL process essentially reinforces the reasoning steps, the COTI, that lead to high-reward outcomes. It's like a coach reviewing game film with a quarterback. The coach doesn't just say good throw or bad throw. They say, see this read you made here. That led to the touchdown. Let's reinforce that thought process. The RLFT is optimizing the entire thought-to-action sequence using environmental feedback.
Building on what Expert 2 said, this RLFT approach showed clear benefits across the board in their experiments: multi-armed bandits, contextual bandits, even tic-tac-toe. It consistently lowered the regret, which is the difference between the LLM's performance and the optimal strategy. Specifically, RLFT demonstrably increased exploration compared to the base models. For instance, the 2B model's action coverage jumped significantly after RLFT. It also helped counteract the frequency bias, making the model less likely to just copy common actions, although it didn't eliminate it entirely, especially for highly repetitive contexts. And crucially, it seemed to narrow that knowing-doing gap.
So RLFT pushes the needle: better exploration, less bias, more alignment between thought and action. But I sense a but coming.
There's always a but in research, isn't there? Laughs yes. While RLFT improves things, the paper is quite clear that the exploration strategies learned purely through this COTI-based RLFT are still, well, suboptimal compared to classic, dedicated exploration algorithms like UCB. And this leads to my contrarian, or perhaps just more cautious, take. Is the fundamental architecture of LLMs, being autoregressive predictors trained on static web text, inherently misaligned with the dynamic, trial-and-error nature of exploration? RLFT patches the problem, but maybe we're fighting the model's core instincts here. We see it knows what to do, but the ingrained prediction mechanism struggles to take that uncertain, exploratory step.
That's a provocative point, Expert 4. If RLFT alone isn't enough to achieve optimal exploration, what else did the researchers try? Expert 1, from a practical standpoint, what were these additional exploration mechanisms, and do they seem viable for business applications?
This is where it gets really interesting from an application viewpoint. They tested a mix of classic RL techniques and LLM-specific ones, things like standard epsilon greedy, where the model just takes a random action a small percentage epsilon of the time. Simple but effective. A trial strategy, mimicking how UCB starts basically, force the model to try every available option once before settling into its learned strategy. This worked surprisingly well. Then more LLM-centric approaches like self-correction, where the model generates an initial thought action, then gets prompted to critique and potentially revise it. And self-consistency, where the model generates multiple reasoning paths and picks the most common resulting action, kind of like crowdsourcing its own thoughts. But the one that really stood out, especially combined with RLFT, was adding an exploration bonus. Simply giving the model a small reward bump for trying an action it hadn't tried before during the RLFT process significantly boosted exploration and performance, getting it much closer to the optimal UCB baseline. From a business angle, the trial strategy is appealing for its simplicity, assuming the initial exploration phase isn't too costly. The exploration bonus via reward shaping seems powerful. It's like setting the right incentives for the behavior you want, a classic management principle. As Peter Drucker might say, what gets measured gets managed. And here, explicitly rewarding exploration gets you more exploration.
In Expert 1, your point about the trial strategy working so well is quite telling. It reinforces Expert 4's concern. The fact that LLMs perform neuroptimally if you force them to gather initial information suggests their main weakness isn't decision-making per se, but rather the proactive exploration needed to inform those decisions. They're like brilliant analysts who need someone else to hand them all the relevant data first. This also connects to another key finding, supervised fine-tuning SFT on expert data. They created datasets using the optimal UCB algorithm, including its reasoning steps, thought cloning. Fine-tuning the LLM on this expert data led to near-optimal performance, basically mimicking the expert perfectly.
That's a double-edged sword for business, isn't it? On one hand, if you have access to expert demonstrations or an optimal oracle for your specific decision task, SFT looks like a very direct path to high performance. Think training a trading bot on successful historical trades. But for many novel or complex problems, that expert data just doesn't exist, or generating it is prohibitively expensive. That's where RLFT, despite its imperfections, becomes more attractive. It learns from its own experience in the environment without needing a predefined perfect playbook. It's the difference between learning from a textbook versus learning by doing.
A classic build versus buy, or in this case, learn from expert versus learn by doing dilemma. Let's shift gears slightly. Expert 4, the paper touched on thinking time, the computational budget for generating the rationale. What was the impact there?
Yes, the generation budget, denoted as G. They found that giving the model more tokens to generate its COTI rationale during RLFT generally improved performance. A model allowed 512 tokens for reasoning did better than one limited to 256, which did better than one limited to 64. It suggests that more thinking, more steps in the chain of thought, allows for better rationalization and decision-making, echoing findings in other areas like mathematical reasoning. The model literally performs better if it has more space to work through the problem. But here comes that, but again, this isn't free. More tokens generated per step means slower interaction, especially in sequential decision tasks. If your LLM agent needs to make 50 decisions, and each one involves generating 500 tokens, well, let's just hope the user is patient. Chuckles it creates a direct trade-off between decision quality and computational cost latency.
Yes, the please wait. Our AI is thinking really hard. Notification might not go over well. So, balancing performance and efficiency is critical for real-world use.
And this computational cost is a significant factor, especially when considering the potential of newer architectures. The paper rightly points out that the multi-step nature of decision-making coupled with long generation times for COTI makes rollout generation a bottleneck in RLFT. Perhaps architectures like recurrent models. The paper mentions XLSDM as a possibility, which might offer faster inference, could be promising alternatives for agentic tasks down the line.
Fascinating point. Okay, let's bring it back to the business impact. Expert 1, considering these advancements, RLFT, better exploration techniques, the potential of SFT. Where do you see these more capable LLM agents making a real difference soon? And what are the remaining hurdles?
I think the initial applications will be in areas where decisions are complex, but perhaps slightly less instantaneous or safety critical. Think sophisticated customer support routing, understanding nuance and directing to the best resource, not just the first available. Personalized education modules that adapt based on student interaction patterns. Dynamic inventory management based on real-time signals. The hurdles remain significant, though. Beyond the technical challenges of exploration and efficiency we've discussed, there's trust and explainability. Can we trust these agents with important decisions? Can they explain why they made a choice, especially if it goes wrong? Then there's safety, robustness against unexpected situations or adversarial inputs, and the cost of continuous fine-tuning and monitoring. Adoption isn't just about capability, it's about reliability and governance.
I'd add that moving beyond the relatively simple environments like bandits and tic-tac-toe is crucial. The real world is messy, stateful, and often requires long-term planning. Testing these RLFT-enhanced LLMs on more complex benchmarks, like crafting tasks or web navigation agents mentioned in the paper's future work, will be key. And as we consider deploying these in higher stakes scenarios, finance, healthcare, ethics laden choices, the need for robust, reliable, and perhaps even value aligned decision making becomes paramount. This might require more than just RLFT. It might involve integrating symbolic reasoning, causal inference, or more structured knowledge. The journey towards truly autonomous and trustworthy LLM agents is still underway.
A perfect note to end on. It seems clear that while LLMs have incredible potential for agentic tasks, their inherent decision-making flaws require sophisticated solutions like RLFT combined with smart exploration strategies. The path involves navigating trade-offs between performance, cost, expert data availability, and tackling fundamental challenges around exploration, trust, and safety. Huge thanks to our expert panel, Expert 1, Expert 2, Expert 3, Expert 4, and Expert 5, for shedding light on this complex and rapidly evolving field. This has been incredibly insightful. And thank you to our listeners for tuning into Catalyst Conversations. Join us next time as we continue to explore the intersection of technology and business. This paper investigates why large language models often struggle with decision-making tasks. Researchers identified 3 common failure modes. The first is greediness, where models prematurely stick to known good options. This greedy behavior limits exploration of the action space. The second failure mode is frequency bias, seen more in smaller models. Frequency bias means models copy common actions from their input, even if rewards are low. The third issue is the knowing-doing gap. This means models can explain a correct strategy, but fail to execute it properly. Models often generated correct reasoning, but still chose suboptimal greedy actions. To address these issues, the researchers proposed a new method. They used reinforcement learning, fine-tuning, on model-generated reasoning. Reinforcement learning is a method where models learn from rewards and penalties. The reasoning used a technique called chain-of-thought prompting. Chain-of-thought helps models outline their thinking step by step. The fine-tuning process adjusted the model based on rewards from the task environment. Experiments were run on multi-armed bandits and tic-tac-toe game simulations. Multi-armed bandits are simple problem testing exploration versus choosing known rewards. Results showed reinforcement learning fine-tuning improved the model's decision abilities. The fine-tuning increased exploration behavior. It also helped narrow the knowing-doing gap. The method successfully reduced greediness and counteracted frequency bias. Chain-of-thought reasoning proved vital for effective fine-tuning. Different exploration strategies were also tested during the fine-tuning process. Simple strategies like trying all actions initially improved performance significantly. Adding a small reward bonus for exploring new actions also worked very well. Fine-tuning with expert examples led models to perform almost optimally. Giving models more processing time to think also improved results. The study mainly used small to medium-sized language models. The task durations were somewhat limited. Future work should explore larger models and more complex tasks. The high computational cost of this fine-tuning approach is also a consideration.